Haris, are you there? You can start sharing your screen. Okay, Haris Dapo is an example case, I would say, of what we try to achieve with the project at Sarajevo. He finished his studies actually at Sarajevo, and he's now in Ankara. So actually, from there, he got involved already with the project in Sarajevo, and he did already some calculations with FLUKA on the safety and radiation protection issues for the room that we want to see. He's going to give a more general presentation here. Thank you, Haris. You can go on.
Thank you. Okay, so like Jutta said, my name is Haris Dapo. I'm a former graduate of Sarajevo University. Currently, I'm working in Ankara, having both positions at Ankara University and Turkish Accelerator and Radiation Laboratory, Tarla. And today I'll be talking about radiation safety planning with FLUKA. After some introduction, I will explain briefly a few generic FLUKA applications and then move on to the sort of setup or what it is that we need in regards to radiation safety in such accelerator facilities. And then I'll present 3 examples, one of which will be the actual current project of Sarajevo ion beam accelerator. And at the end, I will summarize. So first of all, let me start with the general website of FLUKA, as well as the list of the main authors and the contributing authors. I'm a user, so I'm no great expert on FLUKA. Today we'll have a proper contributor later on in the later session. So if you have questions about code, those are better directed there. But I then focus on this combination of using this Monte Carlo program or tool set to see how to deal with actual problems or actual situations in laboratories. The complete list of entire FLUKA collaboration is much bigger than what I've just shown there. And as you see here, both CERN and IFN are the main contributors, but there are many other contributors. So what is FLUKA? So a very short description. So it's a tool. It's a purpose tool for calculating particle transport as well as interactions with the matter. So here, matter can be anything from static walls and steel and similar to something more dynamic, which is tissue and similar. It is coming from a kind of high energy physics background where the particles that are being simulated are mostly then above some keV range and includes then all the way up to, as you can see here, some tens or hundreds of thousands of tera electron volts. It has the full set of all the particles that we know appear at up to these kind of energies, both hadron-hadron interactions, electromagnetic interactions, nucleus-nucleus interactions. For most applications in nuclear physics and then radiation physics, you wouldn't be dealing with such high energies. Something up to a GeV is all you will reach. So some of the more hypothetical particles will be out of the question. The second part of it is then this matter interaction where you're simulating both detectors or shielding issues and similar. So their issues, for example, like neutron transport and such are of very high importance. For the applications in medical physics, one advantage of FLUKA is this ability to deal with voxels of geometries, and there are even ways to import geometries directly from the PET camera or similar diagnostic devices. The last thing that eventually attracted me to FLUKA as opposed to programs like Giant and similar is that it's much more user-friendly. It's kind of low-level coding where you're dealing with parameters rather than explicit coding that you have in programs like Giant. And on top of that, FLUKA has this nice graphic user interface with which is paired with FLUKA, which is called FLAIR, which I'll talk a little bit later on. So what is then FLUKA and what is its code design? So it's a Monte Carlo simulation. That means what you're doing is you have random numbers, actually pseudo-random numbers, and you're then trying to generate events and particles along the line of your trajectory of the particle in a kind of a statistical fashion. So there you have this concept of condensed history, which is essentially just saying that you have statistics. So everything is statistical. It's not a single event, both in terms of, let's say, if you have a beam which has a huge number of particles, let's say 10 to 16, 10 to 17 particles, there is no chance that you can simulate all of them. So you're statistically approaching both the number of particles, but also along its trajectory. If you have many interactions, for example, if you have protons, which have a very short mean-free path, they will have very frequent interactions. And there also you're looking at some sort of condensate kind of an average, so to speak. Now, most of the input into the FLUKA is then microscopic models, which often rely mostly on theory. But of course, both models themselves and FLUKA is then compared to data, and it's kind of benchmarked with data. The advantage of FLUKA is that it integrates all these physical models, so you don't have to care specifically if you're using this or that physical model of, you can do such things in other programs. Here, they're all integrated, so you don't need to sort of choose a physicalist. You kind of have a preset, which then suits best your applications, and there you have a couple of choices. What you can, however, optimize and do is how you score things. So certain regions can be more important, certain regions can be less important, certain particles can be more important and similar. This then allows you to optimize both for accuracy as well as for CPU use. You can get FLUKA from their website. This is, you would have to register. The FLUKA is free for academic users, but you do need to make a registration. This is the latest options in terms of architectures. Typically, FLUKA relies on Linux and various versions of Fortran compiler. The recent version that I'm showing here is from 11th of April. I just got the mail 2-3 days ago that there was another yet more recent version. So this information is already outdated as of this week, but it's reasonably simple to understand if you're familiar with your own system, what it is that you need, which of these particular packages that you should use. So, okay, a word about FLAIR. So FLAIR is a graphics user interface intended for FLUKA. You could use FLUKA without FLAIR, obviously, but then there's a bit of a higher threshold for entry because the raw text form of FLUKA does not warn you of certain mistakes that you may make, whereas FLAIR is very helpful there. So it has a lot of tips and tricks and help, which warns you when you have made a mistake in your input of parameters, and this then you can immediately and quickly correct. The most crucial one is then about geometry. You don't want overlaps of your geometry which are unphysical, protrusions of one region to another. And this is something that both FLUKA in general, but FLAIR in particular, can easily warn you about. You have here you see how this input looks like. You define your beam position, various geometry patterns, and later on you then define specific particles that you're transporting and looking at. And also here you then also define what it is that you're scoring, what it is that physical quantity of interest that is interesting to you is the one that you're saving. So this becomes all rather nice. On top of that, FLAIR then includes ports for running the program where you can easily run multiple copies of your program. as well as then porting things to plot them. This is done through either MATLAB or typically, or more conveniently, GNU-plot. Most of the graphs I will show later were generated then in this way through Flare and GNU-plot. So this is, for example, what you can see if you look at geometry of FLUKA. You have imported a phantom, a human phantom, and then you see at the delivery of energy or dose at the particular point in the phantom. You can do, again, more sophisticated things, but this is just to give you an illustration. One thing that FLUKA also includes is this standard of imaging, which is related to medicine, which is DICOM images, as well as this voxels, which are coming from the patient or phantom. Okay, so let's see a few generic FLUKA applications. So this is a collimator from LHC. A collimator is just a region through which is non-accelerating, through which you're transporting your beam. That beam may be, let's say, neutrons or some other particle. Here, what we are actually looking at is, as you're using this collimator, especially if your energies are high enough, the material of the collimator will become activated. So you'll have permanent radioactivity induced in the material of the collimator. So then what you want to understand is when you switch off your beam, and here's you see cooling time, after which time is it safe for me to approach this machine? So this can be very short, a few minutes, up to some scale of, let's say, 4 months and so forth. So here, the beam is coming from the right, or was coming from the right to left. This is the off beam situation. And now after 8 hours of cooling time, you can see all the dose which is being generated in the area surrounding this collimator, which can be a little bit too high. So millisieverts per hour, as I will explain later, is a little bit high, but if you wait a couple of months, then it drops to some more manageable levels, and some of the areas around here, as well as these bluish areas, you could approach safely. This also then relates not just to maintenance, but also decommissioning of such facilities. I will later show one of our components where one of the issues was also, once you have used this for, let's say, 5 years, 10 years, 25 years, how long do you have to wait till you can take this out of the room? This is not as big of an issue for accelerators, but in, let's say, nuclear reactors, this is a very, very important issue, and decommissioning is a very, very important part of the planning for a nuclear power plant. Dosimetry applications is something which is routinely done in FLUKA. Here is an example of actually not an accelerator or a reactor. This is an example of a flight. Two planes, one from Seattle to Hamburg flying over the pole, Seattle to Hamburg flying over the pole, and one from Frankfurt to Johannesburg flying over the equator. And you can see in the upper part, in this case, it was just simulating neutrons and the dose generated by the neutrons coming from the cosmic rays. And here you can see that in the case of Seattle-Hamburg flight, this is higher compared to the Frankfurt-Johannesburg flight, which is lower. Both for Sarajevo, since it doesn't have such a long history of accelerator use and dealing with radiation, but in general, when you're dealing with non-experts, radiation, as we have seen actually in the change of the name from nuclear magnetic resonance to magnetic resonance, people are often afraid whenever you mention radiation or nuclear physics. And such illustrations, if you say to somebody, will you take a flight from Seattle to Hamburg? Everybody would say yes without blinking. But then when you say to them, would you approach my accelerator? They will say, of course not. But if you tell them that your flight is more dangerous than my accelerator, then this kind of stops them in their tracks and give them something to think about. So two levels which are of interest, which I'll show later, I denote here in the picture as well. So that's 2.5 microsieverts per second and 0.5 microsieverts per second. I will explain their significance a bit later. And the main topic of this conference, this is the proton and carbon ions. This data taken from HIT. So here you see this Bragg peak nicely reproduced by FLUKA, as well as the squares, which are experimental data. This is a proton at energy of 183, and you see that it penetrates in water, and humans are pretty much water, only about 200 millimeters or 20 centimeters. So when you go much lower energy, this will shift far to the left. Similarly, in case of carbon atoms, carbon ions, FLUKA once again reproduces the situation rather well, and not only the primary peak, but also here in the blue line, you see the secondary fragments, which are coming from the interaction of the primary beam, carbon beam, with the tissue, with the patient. And here you see all these secondary fragments from hydrogen all the way to carbon, which are then in this post-target region, which are in principle creating the undesired dose in the tissue that you don't want to irradiate. FLUKA also captures this piece as well. If you then look at actual example of planning, here is how it looks in typical treatment planning program. What one pencil beam that you're delivering to a tumor, and this is what FLUKA can do. And this was all the way back in 2007, so FLUKA can do much more nowadays. Okay, so to move on to radiation safety. So what is radiation safety? What is that we are looking for? So here the goal is to create a guide for planning and implementation of radiation protection program. And this part, the planning part, is where FLUKA can really help the most. So in general, the goal with radiation safety is this ALARA principle, where you want to keep your dose rate as low as reasonably achievable. And of course, the true criteria is that you do not exceed some specified safety limits. So what you want to do is you look at various particles, various sources of radiation that you have, and you want to kind of have a balanced treatment that you're shielding both against photons, neutrons, protons, or etc. Often, especially for example in the case of Sarajevo, where the beam energy is rather low, and this is after the RFQ, not even just the gun. What you're limited to is giving order of magnitude estimates, but even these are a good guide to help you to understand your problem and to prepare for any kind of eventuality in terms of safety that you may have. So altogether, FLUKA can help immensely to ensure that measures to avoid accidents and implementation of ALARA is done effectively. A few words about units. I'm assuming most attendants know these, but the interesting ones is then gray, which is the absorbed dose, which is principal energy. Equivalent dose is also kind of energy, again in joules per gram. The difference between these two units are these RBE factors, which we heard in the previous days, where it is not the same if you get 2 grays of photon dose compared to 2 grays of proton dose. This also then goes the other way. Again, as you've seen, if you want to be more efficient, you work with protons, then in that case, you can deliver fewer grays. Another unit that we will need is then the activity. That's just the case per second and is known as becquerel. Some words about terminology that we'll use. So controlled area, supervised area. The controlled area is where you're focused on. So this is the region where you're actually doing specific protection. You want to control exposure as well as prevent spread of contamination under normal working condition. Contamination is, for example, if you have any kind of dust, which may become activated, and now people are working on that dust and spread it around, or if you have a spill in terms of liquid, and again, this exits your controlled area. The ultimate goal is then to prevent or limit the extent of potential exposures. Supervised area is less than controlled area. There you still have to think about what is the radiation, but in general you could think about letting people who are not radiation workers enter this area under certain conditions. All of this is then supervised and done by a radiation protection or a radiation safety officer. So a word about these limits. So typically the ICRP sets limits on how much dose a radiation worker can get. So this is done at kind of a world standard, which is 20 millisieverts per year, provided that no 1 year exceeds 50 millisieverts. This is essentially a compromise because there's a difference in rules between EU country and Switzerland, where it's limited to 20 millisieverts per year compared to the United States, where it's 50 millisieverts per year. In both cases, the dose limit for general public is 1 millisievert per year. Okay, so how do you then translate these dose limits into time? So I want to answer how long can I spend in this particular room, which has this particular dose. So there you have to take 3 factors into account. Is your accelerator on or off? So workload. What is the orientation of your accelerator? We have seen that you can rotate the beam with various gantries. So it's not the same if the gantry is in the down or the up position. In that case, you have to worry about those people which are below or above if your accelerator has upper and lower floor, or commonly to the left or to the right, because typically you have rooms to the side, as well as then this occupancy factor. So how often is somebody in this particular room? So the workload is based on how often the accelerator works, and unlike CERN, most accelerators don't work 24/7. They're on and off. Especially in medical context, you are only delivering the beam to the particular room during the time the patient is there. In the time when you have preparation, when you're positioning the patient, or post-radiation beam is obviously not on. In the case of accelerators which are research-based, typically then you don't consider this workload as workload of the machine, but workload of the people. And in that case, it would be, let's say, a 40-hour week, which is typical for most countries. Occupancy factor is then you want to distinguish areas, for example, where people are permanently sitting, a work area that will have an occupancy factor of 1, compared to some corridors or elevator where you think of 1/4 or 1/3. Again, difference between different countries and standards, as well as any other area, for example, a storage shed, which is entered maybe once per week or once per month. There you can assign a factor of, let's say, 1/16 or 1/10. This, as I said, the orientation factor in U is 1 for research reactors, which are often fixed. But if it's rotating, then you have to take that into account as well. So this is then best explained by an example, and I took here the example of CERN, where CERN classified various areas of its facility with non-designated, so then anybody can enter, and there you still have to monitor and see what are those levels. If it's a workplace where, let's say, a secretary is working, you consider about 0.5 microsieverts per second. If it's a corridor, then it'd be 2.5. If it's supervised, so there's people entering, but it's still not radiation workers, it can be 3 microsieverts per hour. And then if it's truly radiation workers, then it's 10. This is then derived based, these numbers are then derived based on the total number, which is 20 millisieverts per year, as well as taking into account the workload, orientation, and occupancy factors. I circled the ones which are typically most interesting or most limiting for radiation safety, because once you go to these limited stays and high radiation areas, there other factors will be more limiting, and you can only, let's say, you need only to worry about these, but you don't design by these. And obviously an area where you have more than 100 millisieverts per hour would be strictly prohibited from entering and would be non-accessible. Okay, so let's move on to the 3 examples that I mentioned. So first one will be my main facility here, which is the Tarlas Electron Linear Accelerator. Here is the area of the nuclear experimental station. This area is the main LINAC hall. Free electron laser, which will be constructed here, is in this area. And I also pointed out the area of the electron beam dump, where in case of working is the highest source of radiation. The LINAC has some parameters. So at most it delivers 40 MeVs and 1.5 milliamps. It has various other parameters in terms of beam parameters, but we are not so interested in that one. In addition to this main LINAC area, we have as a side here my second example, which is the medical LINAC. So here medical LINAC means gamma or electron source, not a proton or a heavy ion source. This is a machine which was donated to us by the local Ankara University Hospital as they were decommissioning it. And we use it now and wish to use it for research. So there is no patients here, but still there are issues of radiation safety. So a few words about Tarla before I move on to the radiation safety. So Tarla is located about 15 kilometers south of the Ankara city center. It was founded as part of Ankara University and slowly grew from center to the institute. And now finally, since this year, we have separated from Ankara University and became a national laboratory. We are currently in the process of this administrative restructuring. Its goal is to construct a superconducting electron LINAC, and with the intention to use it for nuclear radiation physics, as well as to generate this free electron laser. Tarla is designed and intended as a user facility with the intention of welcoming users from all over the world. LINAC, provided COVID doesn't interfere again, is set to be completed in about 9 to 12 months. We were in fact supposed to be completed at the end of this summer, but we are now almost 1 year delayed due to COVID. This administrative restructuring should be completed in about 6 to 9 months. So I wish to use here a little bit of chance to advertise that in about that time, 6 to 9 months, we'll be hiring about 7 to 9 young scientists. So please keep an eye on our websites. Past that, in the next spring and summer, we will also be hiring or offering scholarships to students. So in that period also, you can interested students can check out our website. So this is how assignment of what area is prohibited, limited stay, or work area is done for Tarla in case when the beam is on. So this area of the accelerator is clearly off limits. Everything is closed, then you cannot enter it, but you could enter provided that the beam is not inserted into these 2 areas. But this is designated as limited stay, as protection is in this area is not ensured to the same level as, for example, in here and here, where it's designated as the work area. The rest, the corridors and such, are accessible under supervision. Okay, so one of the main things that we had to design here, as I said, main source of radiation would be the beam dump, where during the working of the accelerator, the majority of the beam power is deposited. You have heard, obviously, in previous lectures that in typical accelerators, most of the beam is not used. In case of this electrolytic accelerator, typically we use only less than 1% of the beam, so 99% of the beam is continuously being deposited into the beam dump. So To plan both the beam dump as well as the safety here, I'm showing you here actually the 5th iteration. So this is the 5th design that we had. And each of the stages went through some simulation of FLUKA. If you think in terms of software, this is beam dump 5.0. Design parameters that we chose are slightly higher than that of the actual beam for 2 reasons. One is to induce a kind of safety factor. And 2 is, should there be later on an upgrade of the LINAC, the beam dump can still work. So instead of 40, we went with 50 MeV for the electron beam power, and instead of 1.5, we went with 1.6 milliamps current. So that converts the power directed to the beam dump from 60 kilowatts to 80 kilowatts. And now the questions are then to be resolved in FLUKA, which material is used for the beam dump, how to shield this beam dump, and then to make an estimated dose map, as well as to find solutions which are practical. I make a note here that the walls here are about 2.25 meters, but here this distance is not actually 2.25, and this created a problem. So let me show you. Here is then the total equivalent dose as delivered by the beam into the beam dump during operation. And you notice here that we have rotated our beam dump because this distance here to this distance here is less than 2.25. And one of the previous versions of the beam dump oriented in completely parallel to the x-axis gave unacceptable doses in this region. So then a simple solution that we thought of was to rotate our entire design. To see where the majority or what is the major particle in question here, we also looked at what portion of the dose, actually dose rate, is coming from the photons, that's the upper graph, and what portion is coming from the neutrons. So in this case, it was clear that photons are the major problem and not neutrons. We planned that this initial region here is made out of lead, which is better for photons, and only the second region is made out of concrete, which has a comparable shielding power for both photons and neutrons. At the end, we chose 60 centimeters of lead and 60 centimeters of concrete in this direction and 30 and 30 in this direction. We have a little bit of dose rate here, but we decided not to do anything about it because this place is foreseen for cooling tanks, water cooling tanks, and it will be inaccessible anyway. So this little bit of higher dose here is not an issue. However, we still have not dealt with the blowback. As you can see here in this backward angle, we still have dose rates which are too high. So we have to figure out either to insert additional shielding inside the beam pipe or to have shielding in this region here. So this question of the design of the beam dump and shielding on the beam dump is still not completely finished. Probably there'll be one more iteration 6.0 where we will try to resolve these issues here in the blowback region. So this is the case when the beam is on. Second case is when the beam is off. So your beam dump, which is made out of aluminum, which is another choice we made based on simulations, also gets activated. 50 MeV is far higher than separation energies for all elements. So clearly you will have some transmutation. In addition to that, transmutation will occur not only in the beam dump itself, but also in the shielding material. In this case, we considered only the near lead shield to see what kind of activity is induced there. And in the beam dump, the majority of activation goes to the sodium because the beam dump is aluminum. And then this is all the isotopes that you can actually see from all the way from sodium down to tritium. But in addition to this portion of the activation, which is here in becquerel, you also have the activation of the shield Here is a little bit of activity coming off of the lead, but a much greater activity is coming from antimony, because typically lead shields come with about 4% antimony, and even though it is order of magnitude less present in the shield compared to lead, because it's easier to activate, especially very convenient to capture neutrons, antimony provides a significant amount of activation. However, once you look at the dose rates, the concrete shield as well as the lead shield from the beam dump provides sufficient shielding such that in the off state we can still enter the room. So there is no danger. So this is after 1 minute. So here you can't read it, but it's 1 minute. After 1 minute after beam off, it is safe enough to approach the beam dump and we can enter the room. Of course, due to various other reasons, typically for safety, we do not enter the room so quickly, but theoretically we could enter after 1 minute. So this is then the second example of our facility here at Tarla, and this is the medical LINAC. So this is the typical medical LINAC room with its photon source in the center at 18 MeV, and it too then can create activations and has both photons and neutrons as sources of radiation. So as I said, this was a decommissioned medical LINAC which was transferred to Tarla for research use. Unfortunately, due to space limitations, we couldn't use this space for this labyrinth. So what we did is we made a thicker door with more lead than is typically used in a medical LINAC facility. However, once the regulatory agency came to approve our design for license, it turned out that at the very corners, here and here, there was an issue. So the thickening of the door worked at the face of the door that was measured at about 5 microsieverts per hour, which is fine for radiation workers. But at the corners, it went to about 20, and at certain points, it went to about 40 microsieverts per hour, which would be unacceptable even to radiation workers. Now, of course, here we could have done many things, like we could have cordoned off this area or so forth, but at the end we wished them to be also because it turned out that this dose rate comes from neutrons, and neutrons are often difficult to deal with and even difficult to measure. So the regulatory agency was a little bit nervous and said, please, can you look into some solutions where the dose rate would be dropped. So then first we had to confirm that it's neutrons. That turned out to be true. But the question was, where are they coming from? So either they're coming from this wall here as a kind of a scattering in this direction, or it's multiple scatterings going along the entire labyrinth corridor. And then how to eventually reduce those. Either we reduce the width of the corridor, or we further thicken the door, or some third solution. So one that I proposed was to simply add a little bit of shielding here based on this simulation. So here mostly, so here what you're looking at is neutron flux coming through the corridor. Here's the entire view of the entire room for the neutron flux. As you can see, there's some neutrons here. This is in arbitrary units. So because in a medical LINAC, you're not monitoring your primary beam current, so we could not say exactly how much dose we had in front of the door, but at least we could understand through the simulation, is it sharp angles like this or shallow angles like this? And it turned out that it's mostly shallow angles. So my proposal was then to add just some paraffin, about 5 centimeters of paraffin, to the sides or to the very last 5 centimeters of the labyrinth corridor. And this is a little bit special paraffin, so with 5% boron, so borated paraffin. And once we did that, the dose rate dropped even at the corners to 2 microsieverts per hour, and the regulatory agency was satisfied and gave us the license. So this is then the second example where the work has been completed essentially. So FLUKA provided enough information for us to solve the problem. The previous one is ongoing, and the next one is then the very early stages. So first simulations for the Sarajevo Ion Beam Laboratory. Here, it is not photons and electrons, electrons as primary beam, it's protons and ions. After RFQ, it is at most planned for to be 2 MeV. I took a very high current actually, so we are not expecting such a high current. So for simulations, I used 160 microamps. Typically, you expect maybe 10 times less. And then later on, because at these initial stages, it is far more prudent to go order of magnitude estimates than to be something more precise. As I mentioned in our first simulations, there we had small safety factors going from 40 to 50 MeV and 1.5 to 1.6 milliamps. But at the very first, so design of the first, beam dump 1.0, we went as high as 100 MeV and 16 milliamps just to see what's sort of going on and what is that we need to worry about. So this is where Sarajevo Ion Beam Laboratory is. So it's still at very early stages. So even at here, we can designate certain areas in certain ways. Clearly, same color coding as before. So the green would be open access, whereas beam on the main beam area would be prohibited, and the control room would be workspace. Now, in the off case, what you want is that everything is green and only the main LINAC area is a little bit supervised due to potential activations. As I said, typically these would be small with such small proton energies, but still, again, to be on the safe side. Okay, so this is then just design. So these walls here, even though they are full on this drawing, they are actually not full. They are made out of concrete blocks, which are hollow in the middle. So what you do is a little of concrete with some air in between. And then the question is, what is the situation? So if I put a proton beam onto some target, what do I get here? Would this be sufficient? Do I need additional shielding? Or is this room usable at all? So it turned out that, again, we did preliminary simulations, and that showed that primarily particle, the proton, is not an issue from the radiation safety point of view, because if you have seen the previous lecture from Roger Bošković, they have a very, very short range, even in air, a few centimeters. So you can forget about that. But then the primary beam can generate secondaries, so it should be, in this case, protons or neutrons. However, to really estimate how many protons and neutrons you have, here you end up with this limitation of computers that you are not sensitive enough if you run with so many particles. So you have to have some estimates. So what ended up with estimates of something like 10 to the 7 photons per second and 10 to the 8 neutrons per second. Photons, again, turned out to be no problem at all. And then the only issue that then remains is neutrons. So here what I'm showing is then simulations of 10 to the 8 neutrons per second coming off of this point inside this room. And here there are some issues. So there is some shielding necessary. However, if you do a little bit of shielding with just 10 centimeters of polystyrene, polystyrene is convenient because thermal shielding, thermal isolation in buildings is made out of polystyrene. So you just add that a little bit to the wall, and immediately you get a situation which is far, far better. So you conclude that while, yes, neutrons are an issue here, with a little bit of work and a little bit of shielding, it can be handled. So room can be used, but as I said, needs a little bit of shielding. Here, however, I have used, as I said, both for the current, an order of magnitude more, and for the estimate of the neutron production, I used an order of magnitude more. So very likely, My estimates here are at least an order of one or two order of magnitude more than what we are expecting in a more realistic case. Once the ion source is selected and we know that current better, we can come back to these simulations and see in a more, let's say, less conservative fashion what it is that we actually need. The point here is just we can do it. So there is no reason not to use the room. So let me summarize. So FLUKA is a simulation package which can be immensely useful in radiation planning. This is contrasted with the times when people were doing it by hand. So the safety factors that you apply when doing something by hand compared to a Monte Carlo simulation is much higher. So it allows you to be more, let's say, to come up with solutions which are not so conservative. It is versatile and relatively easy to use. Again, there's a little bit of low-level coding, but it's not too much. You have to have a good physics background, so you have to understand what are its limits. And as I said, it is the biggest help in terms of radiation safety is it helps you reduce these safety factors and then to be able to use much more cheap and feasible and more practical solutions. Now, the purpose of it in terms of radiation safety is to reduce reliance on calculation and estimates, but it should be noted that it's no replacement for measurements. Like you've seen in the second example, once you have measured it, you had the dose rate, even though we had planned for a thicker door, we still had to go back to measurements to be sure that the dose rate is what is safe. So while it's kind of a replacement for calculations estimates, it's no replacements for measurements. And with that, I thank you very much for your attention.
Thank you very much, Haris, for this very instructive step-by-step presentation. And you were on time, but now we have to see about the questions. Let's see the document. Can you see them? We share now.
See it, yes.
Very good. So please go ahead and take them one by one.
Okay, so is there a particular reason for FLUKA? Like I mentioned, the reason for FLUKA is, from my perspective, ease of use. Now, nothing is trivial. Everything requires effort, but with good physics background, you can handle FLUKA. The second part of it was initially, when starting to use it, my main concern was photons, less so neutrons. And also over time, FLUKA's handling of neutrons has improved. So the ease of use was the reason why not GEANT, and focus on photons and electrons was why not MCMP. So MCMP is really good, for example, in case of reactors where it handles neutrons very well, although this distinction in recent time has become less. So FLUKA also now handles neutrons very well. But the limitations, actually, GEANT is more versatile and more powerful. But it is more close to true coding, so it looks more like C or C++ coding than FLUKA does. Can phase space file be easily extracted in FLUKA? Phase space in reactions? So in terms of geometries, if that's the question, you can, there are certain options for import as well as for export. Import from this diagnostic elements like PET and so forth are easy enough. For the phase space of kind of basic reactions, no, because that's not what FLUKA is meant for. So you mean like the emittance and similar? Yes, that can be characterized. Yes, you can get emittance or information about emittance later on. Typically, you do have to combine with some sort of hypothetical detector So for one of the things that we've done here is we are going to measure emittance with a YAG screen. So you place a YAG screen with the grid in front of your beam. This was one of the methods discussed, I believe, on Tuesday. And then you get information about emittance. And then this, through other programs, you have to then translate into quantities like phase space and so forth. So what you measure is emittance. What you measure is energy deposition at a particular place. And then you can translate that through other, let's say, data analysis like root and similar to phase space information. Because it's meant more to simulate a detector. So you have to think, how do I detect phase space through emittance and then translate that back into phase space?
Haris, 2 more minutes for the questions.
Okay,
we have to continue the next.
Use full Monte Carlo in the design phase of the facility. Typically it's done component by component. We never do the full beamline completely because of this computational limitation, because if you have too many geometry components, you then run into problems of too long simulations. What we do, for example, we simulate the gun. After the gun, we simulate the dipoles. After dipole injection into the subharmonic buncher, and then after that into accelerating components. So each is done part by part. The full beamline is not simulated because of the limited amount of information you can get from that due to too many geometry elements. But because you know at each stage what is your particle flux, you then go by that. Sorry, I lost the questions.
Yes, I think as we have very short lunch break, we cannot eat more of it. Okay. I suggest if you can type some short answers inside the document with the questions. We have the link in the chat.
Okay.
So now, thank you very much again. That was really great. And I'm sorry for not being able to continue with the questions. We will have...
No problem. I will answer.
And then we go now to our next speaker, Uros Mitrovic from Cozy Lab, who is going